Hello, fellow researchers. In this talk, I'll present our paper, Structured Concurrency, a review. We'll focus on introducing structured concurrency, a technique to write easy concurrent logic that handle cancellation gracefully. In this talk, you can know when and how to apply this technique to your concurrent code. Furthermore, we also conclude the origin of how structured concurrency emerged, which helps to demystify how different terms relate to structured concurrency. Concurrent program is a huge topic. Lots of programming models and techniques have been proposed to solve different kinds of problems. For example, to solve with the problem of communication and synchronization between threads of processes, we got shared state concurrency with lock mechanism to help us. Or you may use a message passing or transaction-based concurrency to help you model your concurrent program. However, structured concurrency aims at a different aspect of concurrent programming. It's a technique and abstraction needed to make cancellation easier. And before we dive into all of this, I think it's better to clarify that structured concurrency doesn't make your program faster. It just makes it easier to write cancellation logic. Here's a question. What will we do if we want to cancel task 2 to 4? The simplest way is to first take in tokens represent those tasks and call some APIs which cancel them one by another. Here's another approach. Instead of cancel those tasks separately, we bind those tasks with an object called scope. In this approach, we cancel a scope instead of a task, and library whoever provides those scope objects will handle the cancellation as a promise. This is how structured concurrency works. Structured concurrency is usually implemented on a library, which provides those scope mechanisms, and the scope doesn't have any impact how your code runs, but will handle how your program ends. Since every library implements structured concurrency differently, this paper concludes the general concepts across those libraries into 4 simple rules. First, a scope can be created at runtime. Second, a task must be bounded to a scope when started. Third, a scope tree represents the state of structured concurrency. Fourth, a scope exits only if all of its children have exited. First rule, a scope can be created at runtime. In terms of structured concurrency, scope manages a group of logically related tasks, and scope can be created by program logic. The second rule, a task must be bounded to a scope when started. Scope is a carrier of tasks, and each concurrent task must be accompanied by a scope when it starts running. In structured concurrency's terminology, we would say that a task is launched under a scope. And here's our third rule. We could represent the relations of your task and scope by a tree-like structure. We call it a scope tree. For any given of time of your program, there exists a scope tree that corresponds to its execution state. A scope tree is constructed by both scope nodes and task nodes with only one constraint. Task node can only be leaf nodes. So we can create a scope or tasks under another scope, but we can only create tasks under a scope. This also shows that scope is a carrier of tasks. And here's a problem emerged from the first 2 rules. A task must be launched under a scope, but since we create scope at runtime, there must be a task which creates a scope to launch another task under it. This chicken-egg problem of which task or scope start first is usually resolved by the library implicitly create a global scope while we enter the world of structured concurrency. Rule 4. A scope exits only if all of its children have exited. As we said before, structured concurrency makes it easier to write concurrent code that cancels a lot. This property of scope is a key to make cancellation easier. By waiting for all of these children exit before a scope exits, we can handle cancellation logic at different level of hierarchy of the scope tree. With those 4 rules, we can show how to write the concurrent logic with the following example. Considering we want to start a service that contains 3 tasks. Once a single task failed, we need to restart all 3 tasks. With structured concurrency, we could write our program as shown below, a function that uses an infinite loop to create a scope and launch 3 tasks under it. For each task running inside the service, while an error occurs, it simply cancels the wrapping scope. Since the actual code may involve more complex startup logic, so we only show a pseudocode here. Even if the code is not real, we can still show how this concurrent code works at runtime. Despite from this paper, we implemented a visualizer to extract how your program runs structured concurrency. The relation of every task and scope can be automatically shown after registering a logger while launching your program, and the actual running result is shown below. The second part of this thesis is about the origin of structured concurrency. We argue that the emergence of structured concurrency is closely related to the evolution of cooperative scheduling, especially coroutines. Although structured concurrency is a set of abstractions independent to any concurrency implementation, coroutines, being cooperative scheduled, is still the simplest way to implement structured concurrency. Since it's a long story, we recommend listeners to refer to the paper for more detailed information. In this talk, we will only provide a simplified version. This is the timeline of how structured concurrency emerged. We think that it all begins with the debate of thread and event, which is a debate on whether to develop network servers based on operating system threads or an event-driven style. Compared to the thread approach, programs that adopt the event approach is said to be tedious to write and not performant for CPU-bounded tasks. On the other hand, concurrent code written with the event approach is much more easier to reason and could avoid some concurrent issues because it is cooperative scheduled. The problem of not tedious to write is solved since 2002, which libraries start to combine the event approach with coroutines. This makes it easier to write concurrent code that conforms the event-driven style. Since the code written in the event-driven style are single-threaded, it should be easier to write and reason because there's only one task they are executing at any given point of time. However, people start to find out that even using such simplified way to write concurrency, programs that associate with cancellation are not easy to implement. Start with 2013. Discussion for those problems came out, and Martin Sostlik is the first one to introduce the term structured concurrency. As a summary, we conclude that the concept of structured concurrency into 4 rules. And we argue that the emergence of structured concurrency is closely related to the evolution of cooperative scheduling, especially coroutine. And for listeners who are interested in adopting structured concurrency in your project, structured concurrency doesn't make your program run faster, but it makes writing cancellation logics much easier. And currently, structured concurrency are mostly implemented on top of coroutines.